Hi, I'm Chris Virox from the University of Florida, and we're Daniel Zoe. Hi, we're Chris Virox from the University of Florida and Daniel Zoe from Reed College. We'll be presenting our work on coalescing particles on a cycle graph. As part of our talk, we'll give an introduction to the idea of a coalescing walk. Then we'll present a couple of examples of coalescing walks, such as the coalescing walk on an interval and the coalescing walk on a cycle. Then we'll present some simulations related to the coalescing walk on a cycle, which will lead us to our main theorem. We'll then prove our main theorem and then discuss a variation of the problem of the coalescing walk on a cycle, known as the annihilating walk on a cycle. We'll then discuss our ongoing and future work. The general idea of a coalescing walk is this. Assume we are given a state space S and a transition function P on the state space S. At time 0, we place a finite number of particles at distinct elements of S. Then at each time t is greater than or equal to 1, we'll choose a particle randomly. We'll then move that particle according to the transition function P, and if the sampled particle moves to a state that's occupied by a particle, we'll combine the randomly sampled particle with the pre-existing particle into one single particle. A particular example of a coalescing walk is the coalescing walk on an interval. The idea is as follows. We're given a graph with a vertex set consisting of vertices 0, 1, all the way up to n, and an edge set consisting of the pairs 0, 1, 1, 2, all the way up to n minus 1 to n. Note that the vertex n is not connected to the vertex 0 by an edge. At time 0, we place a particle at each vertex of this graph, which we call Ln. We'll say a vertex V is occupied if there is a particle at V. Then at each time step t is greater than or equal to 1, we choose a randomly occupied vertex V from the set 1 through n. Note that we will not ever choose the vertex 0, and we move that randomly chosen particle to the vertex V minus 1, combining it with any particle that is already existing at the vertex V minus 1. Note that in this process, all particles will eventually coalesce to a single particle at vertex 0. Here's an illustration of this process for n equals 3. We start with all vertices initially occupied by a single particle at t equals 0. Then at t equals 1, we randomly select a particle from 1 to 3. Remember that we're only selecting particles from 1 to 3, so we're never selecting 0. In this case, we randomly choose the particle 2, a particle at vertex 2, and we're going to move it to 2 minus 1, or vertex 1, as shown here. Since there already was a particle at vertex 1, we simply combine those two particles into a single particle at vertex 1. Then at t equals 2, we randomly select a particle from 1 to 3, in this case, vertex 3. And then we move the particle at vertex 3 to vertex 3 minus 1, or vertex 2, as shown here. Then at t equals 3, we randomly select vertex 1 and move the particle at vertex 1 to vertex 0. And at t equals 4, we randomly select vertex 2 and then move the particle at vertex 2 to vertex 1. Finally, we combine the particle at vertex 1 with the particle at vertex 0. And we see that all particles eventually coalesced at vertex 0. This problem has been previously studied by Michael Larson and Russell Lyons. In their paper, they showed that the expected value of Tn, which denotes the time it takes all particles to coalesce on the interval In, is equal to this expression here. They also show that the variance in Tn is bounded above by this expression given here. Another example of a coalescing walk is the coalescing walk on a cycle. In our work, we'll restrict our attention to this walk. So let's see and denote the n cycle. That is the graph with a vertex set consisting of vertices 0, 1, all the way up to n minus 1, an edge set consisting of all pairs ij, such that j and I differ only by 1 unit modulo n. At time 0, we place a particle at each vertex of Cn, and we'll say a vertex V is occupied if there's a particle at V. Then for each time t is greater than or equal to 1, we'll randomly select an occupied vertex V and move the particle at vertex V to the vertex V plus 1 mod n, so that it's combined with any pre-existing particle at V plus 1 mod n into a single particle. So here's an illustration of this process for the 4 cycle. At t equals 0, all vertices are occupied. Then at t equals 1, we randomly select vertex 1 and move it to 1 plus 1 mod n, or vertex 2. Since there's already a particle at vertex 2, we combine those two particles into a single particle at vertex 2, as shown here. Then at t equals 2, we randomly select the vertex 0, and then move the particle at vertex 0 to vertex 1. At t equals 3, we randomly select the vertex 1 and move the particle there to vertex 2, combining it with the particle already existing at vertex 2. And finally, we coalesce the particle that starts at vertex 2 with the particle at vertex 3. While the problem of the coalescing walk in an interval was previously studied by Michael Larson and Russell Lyons, as we discussed before, as far as we know, the coalescing walk on a cycle has not been studied rigorously. We'll define the coalescence time for the n cycle to be the time it takes for all particles on the n cycle to coalesce. We'll denote the coalescence time for the n cycle by tau n. In the master thesis of Patrick Dichio, it was conjectured that the expectation value of the coalescence time scales as 1/2 of n squared asymptotically, and the variance of tau n scales according to 0.05 times n to the 4th asymptotically. Note that the above results were obtained by computer simulations, so they have not been proven. This leads us to our problem. We're interested in finding out what is the expected coalescence time for the coalescing walk on the n cycle. We first ran some computer simulations for the coalescing walk on the n cycle for different values of n. Our data suggests that the expectation time follows the pattern of the triangular numbers. In particular, our data suggests that the expected coalescence time for the n cycle is n minus 1th triangular number. That is, that the expected value of tau n is equal to n times n minus 1 over 2. This leads us to our main theorem.
To prove the main theorem, we would first like to introduce a method to describe different particle states on the n cycle by looking at the distances between consecutive particles, where Li is the distance between particle I and the next counterclockwise particle. For example, the distance between particle 1 and particle 2 is L1, which is 2. The distance between particle 2 and particle 3 is L2, which is 2. And the distance between particle and the next counterclockwise particle, particle 1, is L3 equals 1. By looking at this method, we would like to make the following observations. First of all, the sum of all the lengths Lk sum up to n. Note that this is true because you always go from particle 1 around the cycle back to particle 1, and since this is an n cycle, they always sum up to n. The second observation is when we move particle I. Let's look in the cycle. If we move particle 2 one step to the right, we will see that the distance between particle 2 and particle 3, which is L2, decreased by 1. At the same time, we will see the distance between particle 1 and particle 2, which is L1, increased by 1. We can generalize this by saying moving particle I decreases Li by 1 and increases Li minus 1 by 1. And we would like to make the third observation. The system ends when there's only one particle, so L1 equals N. When there's only one particle, L1 is the entire cycle, and then the system ends. Now we would like to introduce our main theorem. First, we'd like to define the function S, where Sx is the sum of all integers starting from 0 up to x. Theorem 1 is the expected stopping time for different particle states. We define tau to be the time it takes for all particles on an n cycle, starting at the k particle distribution of L1, L2 to Lk to coalesce. From here on, we will refer to tau as the stopping time. Then, the expected value of the stopping time, Et tau, is Sn minus the sum of all the SLJs. With algebraic manipulation, this theorem implies that the expected value of the stopping time is just the sum of all products of distinct Li's and Lj's. We would like to introduce the concept of a martingale. A martingale is a sequence of random variables xn, where the expected value of xn plus 1, given all the previous states, is just xn. The reason we are introducing the concept of a martingale is so that we can use the many theorems that are already proven for martingales, such as the optional stopping theorem. Now for our first lemma, we would like to define the random variable mt equals SL1 plus SL2 all the way to SLK minus t. Note that the lengths here, L1 to Lk, are the lengths on the system, on the cycle, at time t. So mt is a random variable in respect to time. And the lemma is that this sequence, mt, is a martingale. And here's our proof for the lemma. Assume we are at a time t. For the next time step, we examine the behavior of some length Li. Note that there are three possibilities. First one is when particle I is moved, which occurs with probability 1 over k. Here, Li is decreased by 1. If particle I minus 1 is moved, which occurs with probability 1 over k, Li is increased by 1. And if another particle other than these two particles moved, and in other words, particle I and particle I minus 1 are not moved, which occurs with probability k minus 2 over k, Li does not change at all. Hence, if we take this and then we input it into the expected value of SLI at time t plus 1, we will find that the expected value of SLI at time t plus 1 is SLI plus 1 over k. And since there are k particles, the expected value of mt plus 1, given the previous states m0 all the way to mt, equals mt. And therefore, the sequence of mt's is a martingale. Now for a corollary of the lemma. The expected value of m0 is the expected value of m tau. To apply the optional stopping theorem, the following conditions are sufficient. The first condition is that m tau is a discrete time martingale with stopping time tau. Note that mt is a martingale because we proved it in the lemma, and stopping time tau is as by definition. The second condition is that the expected value of tau is finite. This is true since n consecutive moves of the same particle will go around the circle, coalescing with all of the particles, and it will always end the cycle and create a coalescence. Hence, the probability that tau equals t decreases at least geometrically as t increases, so the expected value of tau cannot be infinite. And that is the second condition. The third condition is that the expected value of the absolute value of martingale increments is bounded by some constant c. Note that we reach our maximum value of absolute value of mt plus 1 minus mt when we decrease the maximum possible length, which is n minus 1, and we increase the smallest possible length, which is 1. And at this case, the absolute value of mt plus 1 minus mt, the largest possible martingale increment, is n minus 2. And therefore, the expected value of the absolute value of the largest possible martingale increment is also less than or equal to n minus 2. Therefore, by the optional stopping theorem, the expected value of m0 is the expected value of mt. And with that corollary, it is very easy to prove our main theorem. Note that when at time 0, we have our original lengths L1 to Lk. So the expected value of M0 is the sum from j equals 1 to k, SLJ. And note at time tau, which is the stopping time, there's only one particle left, so L1 equals n. So the expected value of m tau is just Sn minus the expected value of tau by definition. Therefore, the expected value of tau is as below, and our theorem is proved. And now I would like to present a corollary. This corollary presents a solution to the original problem we set out to solve. The coalescing walk on the n cycle, where a particle occupies each vertex, has expected coalescing time, expected value of tau n, equals the n-1th triangular number, half of n minus 1. This was the original problem, and it's now a corollary of our main theorem. And the proof is very simple. Just let all the Li from 1 to n equal 1, and then the result follows from the theorem. Now I'd like to present a generalization of our main theorem, theorem 1. We introduce a slightly altered coalescing walk with some randomness. At each time step, instead of always moving the particle counterclockwise, now we move it clockwise with some probability p and counterclockwise with probability 1 minus p, where p is between 0 and 1. We denote the system the p coalescing walk. Note that this is a generalization of our original coalescing walk, because the original coalescing walk occurs at the specific case where p equals 0. And our theorem 2, the expected stopping time for different particle states on the p coalescing walk, is just theorem 1 on the p coalescing walk. We make the same claim for the expected value of tau. And for the proof of this theorem, note that in the proof for theorem 1, the only place where we actually introduced how the system works is in proving that MT is a martingale. So if we can prove that MT is still a martingale on the p coalescing walk, then we have proved theorem 2 as well. Note that when we move counterclockwise, the expected value of MT plus 1 given the previous MTs is just MT. And this is from the original proof, the original martingale lemma. And a parallel argument will show that the same occurs when we move clockwise. Thus, the expected value of MT plus 1 given the previous MTs is just P times of MT when we go counterclockwise and 1 minus P of MT when we go clockwise. And that sums up to MT. So the sequence of MT is still a martingale, and our theorem 2 is proved as well.
We'd like to now discuss a variation of the coalescing walk on a cycle. An annihilating walk on a cycle can be described as follows. Let C and B denote the n cycle as before, and at time 0, we place one particle at each vertex of Cn. Then for each time t is greater than or equal to 1, we'll randomly sample an occupied vertex V of Cn and move the particle at vertex V to the vertex V plus 1 mod n. If there's already a particle at V plus 1 mod n, we'll simply delete both the pre-existing particle at V plus 1 mod n and the randomly sampled particle, instead of combining both as before. Note that eventually there will be either 0 particles left on Cn if n is an even number, and exactly 1 particle left on Cn if n is an odd number. We have some results regarding this variation of the problem. Let tau NA denote the time it takes until there's less than 1 particle left on the n cycle for an annihilating walk. If n is even, then the expected value of tau NA is equal to n over 2 squared. This leads us to our future and ongoing work. We have found the expected value of the coalescence time for the coalescing walk on the n cycle. However, we're still not sure what the variance is, and we're currently looking at the problem of finding the variance of the coalescence time. Also, we are interested in finding the higher order moments of the coalescence time for the coalescing walk on the n cycle. As was mentioned on the last slide, we found the expected value of tau NA for the annihilating walk when n was even. However, we're still interested in finding what the expected value of tau NA is when n is odd. We ran some simulations for this problem. However, we haven't identified any obvious pattern in the values of the expected value of tau n a. This concludes our talk. Thank you all for listening.